Hello, so in this video we will talk about the standard uniform distribution. So let's start with the definition. So a random variable x is said to have a uniform distribution if its distribution is given by something like this. So we have 2 points here and we have is the distribution. So this is a, this is b, and it's a flat. So this is some number which is 1 over b minus a. So then we will write it as, if it is PDF, this is given by 1 over b minus a when x is in between a and b. So what is it CDF? The CDF will look like this. We have 0 here, and this line from 0 to 1, a straight line here, and 0 to 1 here. So what is the CDF? So we have x minus a over b minus a if x is in between a and b, and it is 0 before that, before a, and 1 after b. Okay, so this is my fx of x. Okay, now what is the standard uniform distribution? For standard uniform distribution, we have a is equal to 0 and b is equal to 1. Okay, in other words, my CDF will look like this. So this is my 1, and this is my 1, and this is my 0, and this is fx of x. This is equal to x. Okay, so this is x, this is fx of x. Okay, now what we want to show is, we want to show that if we have a transformation y is equal to fx of x for a random variable x who has the CDF of fx of x, then y is standard uniform. This is what we want to show. Okay, so let's start. We will start with like this. We have fy of y. This is equal to probability that y is less than y, correct? Which is equal to probability that fx of x is less than y, which is equal to probability that x is less than fx inverse of y. Why can we say that? We can say that because f of x is monotonic. When a function is monotonic and continuous, then we can have, then its inverse exists. Okay, then we can say this is equal to probability that x is less than fx inverse of fx of x. Why? Because this y is equal to fx of x, because that's the transformation, right? So this and this cancel out, so we can say probability of x less than x, which is equal to fx of x, which is equal to, through this, which is equal to y. So this means that fy of y, this is equal to y. Okay, so this is exactly what we want here. Okay, okay, now, so in order to take now we are generating a log normal random variable with a mean of 0 and a standard deviation of 1, and this Matlab generates it by using this this function, and then we draw the histogram of a log normal random variable. Then using the CDF of log normal random variable, we make a transformation using this function. Okay, note, then we see the histogram of our transformed variable. So now let's see how they look. So note that here we have this distribution from 0 to, let's say, the support, effective support is still 20. Okay, but then we have almost equally distributed numbers from 0 to 1 here. Okay, so this shows that if we use this distribution, this actually does come out to be in between 0 and 1. Okay, now this is for log normal distribution. Now let's change it to exponential distribution. For exponential distribution, we have one parameter only, mu, and mu cannot be 0, so we have to check. Maybe let's use it at 3. So for this one, we have exponential random variable. Again, we use a built-in Matlab function which generates the numbers using exponential distribution, and we do the same thing. Apply the CDF. So the CDF is this function. Okay. So now if you see, same story here, that for the actual exponential distribution we have this kind of distribution here, while for the transform variable we have this kind of distribution from 0 to 1, and each number is almost equally assigned a value. Okay, so going back here, this is about checking if we have if we have this transformation of a random variable, we can have the standard uniform distribution for a transformed random variable. Okay, so this is it about this video. Hope it was easy to understand. Thanks for watching. Hope you liked the video.